I'll talk about this work that I've been doing with Indranil here about the structure of space of conformal field theories. This work, I should say, hopefully is nearing an end, and hopefully we should be able to finish it and write a paper on it soon. So naturally, there would be some places where your input could certainly be beneficial. So please interrupt and let me know if you have any questions. Okay. So let me motivate this work by just motivating the study of the structure of space of theories in general. It's of general importance, and conformal theories in particular form special points in the space of quantum field theories, from where you can think of as an RG flow starting and ending. So during last week, for example, Clay taught us how to think about symmetries of theories carefully, in particular generalized global symmetries of theories, and their anomalies to control such an RG flow. So in general, the question of understanding the space of quantum field theories would be a difficult one, but can we instead ask a simpler but still a difficult question of understanding the space of conformal field theories? Now, the reason to think that such a question would even have an answer that we can get to is universality. So many microscopic systems with different microscopic physics at criticality exhibit same critical exponents, and that leads us to suspect that there has to be, the conformal symmetry is a deep principle which restricts the types of physics that you can have at criticality. And indeed, the modern bootstrap program aims to essentially achieve that, to impose conformal symmetry on a quantum field theory along with unitarity and get constraints to constrain the form of possible critical exponents or allowed physics in general. Now, I've mentioned in passing that such constraints are usually obtained on unitary conformal field theories. So the talk will be about what happens if you relax the constraint of unitarity. The space of CFTs, unitary CFTs, is thought to be discrete unless you endow the theory with additional strong symmetry such as supersymmetry, and then we are familiar with examples where the space of theories is continuous, and that parameter space usually known as the conform manifold. But here we will not talk about supersymmetry, restrict ourselves to just the bosonic theories.
You mean except for trivial examples like E plus 1 conformal field
yes. Yes. But we believe that in higher dimensions, such modulus spaces of theories, conformal field theories don't exist unless you have supersymmetry.
And this is just based on examples?
Yeah, just based on examples. I don't think there is a particular reason to expect that. Okay, so as we will discover in the talk, that once you relax this unitarity assumption, so let me first say that a CFT is QFT clearly with conformal symmetry. And in addition to just the symmetry statement, one can either require or not require two postulates. One is unitarity, and the other is the existence of stress tensor, which would allow you to couple the theory to gravity. Now, this talk will be about what happens if you relax this postulate. We will see that the space will become continuous. In fact, I will argue that there will be a vector space structure that you can put on it. So you will, for theories without, which are not necessarily unitary, you will be able to see how one can make sense of adding two theories and also multiplying by a complex number. So this vector space is over C. Now, as an aside, although it's not going to be the main part of the talk, one can also relax this requirement that there is a stress tensor, so, and talk about generically non-local theories. And even in this case, the space of theories is continuous. Under certain assumptions. So just to give you an example of how such a thing could be achieved, if you imagine that your theory has an operator O, a scalar operator O, with conformal dimension delta, and that d minus delta is obeys unitarity bound, then one can imagine considering a mean field theory or a generalized field theory of an operator phi with dimension delta, which is equal to d minus delta minus epsilon, and perturb this theory by a phi O type of deformation. And just from these dimensions, you will see that this is a relevant operator, and which will trigger a flow and let you find another fixed point, and you can vary the value of epsilon and discover a line of conformal field theories. This, in some sense, generalization of the construction that Richko and Rosselli do to discover the long-range Ising model.
So this phi is what? It's not in the code, it's in some other section?
It's a different theory. It's a generalized free field theory, meaning the correlations of phi are just obtained by weak contractions according to this dimension.
And if we give up, well, this is the case where we're giving up the stress tensor.
Yeah, this is in this case where we are giving the stress tensor, because this theory does not have a stress tensor, so the stress tensor of this theory will be lifted generically by such a deformation.
And the generalized free field theory, apart from not having a stress tensor, obeys all the axioms of
Yeah,
conformal
yeah, yeah. It does. Depending on the dimension, it can also be unitary. I mean, that's why actually I intended this bound, because I didn't want to relax this, but just that.
The spectrum of operators does not include it.
Yeah.
All the conformal symmetry generators are there, but they are not obtained by
Current. Yeah. Right. Mm. Okay, so this was just an aside, because this is another way you could, another relaxation that one could study, and but we will focus on relaxing the assumption of unitarity.
So you say if you give up the stress tensor, then just your generalized free fields themselves form a continuous example.
Yeah, but I wanted to exhibit that there is a modulus for a given theory.
Yeah, I see. But just to have a continuum, just a generalized.
Generalized free fields would do. Yeah, exactly. Okay, so now.
Sorry, I mean, just one more question. Theories that don't have unitarity sometimes arise, I believe, as statistical mechanical models. So those theories typically have a stress tensor.
They do.
Do you know of any use of a theory that is without a stress tensor? I mean, apart from such examples, something that occurs in other.
I mean, in various places we do see main field theoretic behavior also, right? So that could be thought of as just coming from something.
But is there a physical system that is described by a theory without a stress tensor? That you happen to know.
Any mean field theory behavior, basically.
So the Ising model, I mean, you can have mean field theory behavior and the stress.
Right, yeah. No.
You have some connection between mean field theory and not having stress tensor in mind. So
Well, I just by mean field theory I just mean that there is an operator phi with a given with any dimension, and the correlation functions of these operators are obtained by just Wick contraction. And the spectrum of the CFT is obtained by acting on this phi by a bunch of derivatives and taking products. That's what I mean. Okay, so with this as an introduction, let me get into the main topic. For that, let me quickly review some of the CFT language and technology. Perhaps for this audience it may not be necessary, but
that is taking products of derivatives.
yeah. So CFTs, they are formulated in terms of local operators. O of x, and the conformal symmetry leads to.
Sorry to interrupt, one more question. In two dimensions, there are these minimal modules. There's a unitary series, and then there is a non-unitary. So those were also sort of discrete.
Right.
Now, do you know if
yeah, so the reason for that, exactly. The reason for that is that one is not just, so clearly what do they mean, right? What does that, so indeed there is a continuous family of non-unitary theories with C less than 1. But these non-unitary minimal models are chosen by an additional requirement that the spectrum be rational. So as a multiplet of Virasoro, there are finitely many representations. So if you think about it from a Coulomb gas point of view, it will just give you a family of non-unitary minimal models. Okay, so we have local operators in which the CFT is formulated, and then the 2-point function and the 2-point function is fixed, which essentially encodes the conformal dimension, and rotational representation, let's call it spin, and a 3-point function is also fixed up to number. So these statements I believe are familiar, and in addition we have a state operator map.
Three-point functions are fixed up to number for some representation to the
Yeah.
discrete.
Let's see. Some numbers. That's what you mean?
Yeah.
Depending on the index structure, it will have multiple numbers parameterizing a 3-point function of a spinning operators. Okay. So we also have the state operator map, using both these ideas, we can define an operator product expansion.
And that number of numbers can go to infinity as the spin of the operator.
Yeah. So let me just give you an example of the scalar. And this here is just the related to the 3-point function, the coefficient of the 3-point function. Or could be other operators. I just pick out a particular operator. Not necessarily the lightest. Usually we write this in terms of the lightest operator, the most singular terms and onwards. So using operator product expansion, any higher point function can be written in terms of 3-point function, sum over 3-point functions. That is why the entire conformity theory is parameterized by the spectrum, that is the 2-point function, and 3-point function coefficients. So this is known as the conformal data, but because I will be proposing to think about non-unitary conformity series another way, I would call this the conventional conformal data. This is something very basic that I would imagine everyone is familiar with. Now, what consistency conditions does this conventional conformal data obey? Well, if you consider a 4-point function, you could either think of it in this channel where you are summing over the states that separate states on the sphere that separate x1, x2, like so, or you could think in terms of this channel where you are summing over a complete set of states on the sphere which separates x1, x4. And because it's a sum, you are summing over all states, which by state operators one are operators. And both ways of computing the 4-point function should be equal. So this is the crossing symmetry. Now, how is unitarity reflected in the conformal data? Well, the constraints of unitarity are essentially that the conformal dimension of every operator should be greater than some particular function of its spin, and that the 3-point function coefficient be real. And if you do have these unitarity constraints along with conformal symmetry, essentially they mean that that even studying one particular, note that these equations, these are different equations depending on which operators you choose as the external operators. So there are infinitely many of these equations. So roughly speaking, there are, if n, which is infinity, where the number of operators in the CFT, these equations are n to the 4, while the OP coefficients are n to the 3. So it's usually believed that these are sufficient to constrain the conformal data. But even thinking about one bootstrap equation, one crossing equation, which is what one or few crossing equations is quite powerful, which is what the modern bootstrap program is all about, where you consider a few crossing equations or even one crossing equation, and along with conformal symmetry also impose unitarity. And this constraint turns out to be quite powerful and ends up constraining the space of these conformal dimensions to a great extent. One of the main success stories of this program are the determination of the exponents of the 3D Ising model. Okay, but now if you don't have unitarity,
Like, is this the full list of constraints given by unitarity? If these are obeyed, does it necessarily follow that the theory is unitary?
yeah, I think so.
These are obeyed and there is follow.
Yeah.
That's not the proof of that. I mean, clearly unitarity implies it.
Right. Yeah.
But it's the other way around.
So I guess one should prove that all correlation functions are reflection positive coming from this. There should be some proof of it, I think. I don't see a big problem there. In fact, it's embarrassing, but I don't know how this comes about from reflection positivity. We could talk about it later. Usually one appeals to unitarity in the Lorentzian signature to show that this is real, but not reflection positivity in the Euclidean signature. It'd be nice to understand how it comes about. I'm sure it's some very basic confusion of mine. Okay, fine. Yeah, the question is, there are some cases, Shiraz pointed out, like at the Lee-Yang model and so on in statistical mechanics, where thinking about non-unitary theories is also something that you want to do. And how does one think about classifying those theories using such a program? Now, if you relax the constraints of unitarity and try to work in the similar way by taking one or a couple of crossing equations, it turns out that they're extremely easy to solve. So they don't end up offering any constraint on the conformal data. So quick way to see this, what this means is that you want to write a crossing symmetric function of x1, x2, x3, x4, and just any symmetric function of x1, x2, x3, x4 would do. The point of imposing that is that once you expand that symmetric function in terms of conformal basis, these coefficients turn out to be positive, which is a non-trivial constraint. If you, so as I said, if you do relax it, then the usual bootstrap program does not get you any constraints. But nonetheless, there is a way of thinking about such theories, which was first proposed by Gliozzi, also called the Gliozzi method, wherein you take this crossing equation, which is equal to sum over S channel, let's say, minus sum over P channel equals 0. I hope this schematic equation is sufficient to describe what I'm saying. And you just truncate these sums to a particular order of particular number of operators, and the conformal data that is involved in these equations, you also parameterize them by certain physical inputs. So for example, you expect that for the Lee-Yang model, the operator spectrum will behave in a certain way. So you end up parameterizing the conformal data just using a few parameters, and then you have multiple equations, and you just minimize the failure of the bootstrap equation as a function of these physical parameters, and at the values of those parameters where this is minimum, they are expected to give you the physical, give you the right critical exponents of the non-unitary model. And this has been successful in essentially describing 2D non-unitary theories, wherein you input the fusion rules of Lee-Yang model. Now this is slightly counterintuitive, because if you think about it from a mathematical precise point of view, then you see that the sum over operators in the S channel, if you look at the contribution coming from the lightest operator, it is given in satisfying these operator equations by very high operators, very heavy operators on the T channel. So truncating this equation at a particular number of operators seems something weird thing to do, but somehow this seems to work reasonably well. I bring it up because
this condition is that you keep 100 terms in the first sum and
100 terms on the second sum. Yeah, exactly.
And you somehow expand around the self-dual point or something like that? I mean, how do you equate that?
Yeah, you do expand around self-dual point, take a bunch of derivatives, so keep a bunch of equations. It's a matrix valued equation having to do with the number of derivatives and the number of terms.
Yeah. So you're not trying to reproduce the singularity in one channel.
No.
Which, as you say, would be impossible.
It would be impossible. Yeah, exactly.
So they're taken a different subset of putting in first 100 over here and the second 100 over here.
Yes. You're welcome to do that. Yeah. Okay. But nevertheless, this cannot quite be thought of as the classification program, because it needs some inputs that you a priori know. So one wants to have another method of thinking about non-unitary theories. So in this talk, I will propose a way of doing so, wherein I will introduce an alternate set of conformal data in which many of the structural aspects of the space will become manifest. In particular, this will imply that the non-unitary space of non-unitary theories is a vector space.
One general question before you get into the structure. I thought that for static, the reason that these things, conformity theories, were useful was because things were discrete. That's the underlying reason for universality. So if we're now what I'm hearing from you is that if we're not in a unitary situation, then there's no universality.
Yeah, so I don't quite know what picks out a Lee-Yang model, for example.
Right.
Yeah, that's a good question. In 2D, some rationality condition is there. Sorry.
Yeah. So in a particular model that you write down, maybe you know that it's Lee-Yang, but in an experimental system.
Yeah. So probably I will make a comment now, which may be related to.
So if you take an arbitrary, you can take an arbitrary set of numbers that they are spectrum, and arbitrary set of crossing symmetric functions and your focal functions. Okay. And you have enough of these. You get a valid data for non-unitary theory.
Yes. I mean, I guess that's what I will point out. What is this? Because
somewhere the C part of the space is scalar. It's kind of same here. It is entirely that the two-point functions are powerless.
Well, no, but there is a whole consistency of the theory also that one has to think about, right? There are infinitely many 3-point functions, and each gluing of them should produce. So in particular, this equation has to be produced for all operators here. So indeed, if you really want to solve it, you think about non-unitary theories without the help of these constraints. So you really have to solve all crossing symmetry equations, which I said are given by any pair of any set of 4 local operators, and that's certainly a daunting task.
And the way you said it is inconsistent, right? Because you choose a function, then what you get by cutting determines the set. Determines part of it.
It's not a separate.
Also then arbitrarily choose it.
Even if you correct what you said, it's still infinitely many equations that one has to look at. Because there could be, so let's say you're talking about a thing where you have O1, O2, O3, O4, and you just write down a symmetric function, and then there is a, let's say, an O5 here, and that will give you a 3-point function of O1, O2, O5. But now that will also come about when you consider an O5 here, and so on. And now you have to make sure that O5, O2, and O1 it should be the same as before. Okay.
One more question. At the beginning, you suggested some sort of counting, and that suggested that there were more equations than this. And that counting made no unity sense.
Right.
So that might have led us to suspect
that even the unitary
non-unitary theories would be somehow very special and very discrete.
Yeah.
But you're saying that's wrong.
That's wrong. Yeah. Yeah, another comment which is relevant here is that I'm taking a conform field theory to mean a theory which obeys the crossing symmetry equations and could possibly also obey unitarity, constraints of unitarity. But that, of course, does not guarantee the consistency of theory on manifolds that are not conformally related to R4. So in particular, if you were to just use these constraints in 2 dimensions, your partition functions will not come out to be modular invariant. Modular invariance is something that one has to impose in addition to these constraints. And in higher dimensions also, presumably there are constraints coming from requiring consistency of theory when you put it on, let's say, a T4 or S2 times T2 and so on, wherein there is some sort of a global gravitational diffeomorphism that acts, and you require that that also is a symmetry of the theory. So those constraints I'm not taking into account right now. Just if you wish, what I'm trying to solve is the infinitely many crossing equations here without after relaxing unitarity. Okay. Okay. So as I said, I want to come up with an alternate set of conformal data which will make this structure manifest. And without keeping you waiting for too long, I'll just tell you what this alternate set of data is. This is essentially the set of n-point functions of a scalar operator, let's say, of a specific
this by itself cannot be a vector space because they obey nonlinear constraints.
Yeah, so I will clarify what I mean by that the space of CFTs is a vector space. Yeah, this set is not a vector space because so that would be a statement in the CFT itself. I'm making a statement about the space of theories being a vector space. So in particular, I will show how to add a set of these things with another set of, from CFT1 and the CFT2, how to multiply this set by, a complex number and so on. Okay. So clearly, so let me first argue why this is an equivalent set of conformal data. If you do have conventional conformal data, that is the 3-point function, 2-point function, you can glue them to form these n-point functions. So clearly, you can map from conventional data to this data, and vice versa also, because if you are given a set of n-point functions, you can take sequential OP of, let's say, this scalar operator is phi, and you are given, let's say, phi of x1, phi of xn, and then you can take sequential OP of 2 phis to produce complicated operators, in particular spinning operators, and get their 3-point functions, which is the conventional conformal data. So going back to one of the points that Shiraz made, a spinning operator, along with other spinning operators, has multiple 3-point functions having to do with their index contractions, index structures. So it's clear that such a prescription will also give you the right 3-point function as a function of these index structures. So what do I mean by that? So let me clarify what I mean. An operator O, which is in representation R1 of rotational group, operator OR2 and OR3, one wants to compute their 3-point function. And such a 3-point function exists if R1 tensor product R2 tensor product R3 contains a singlet, not of the rotational group, but of SOD minus 1. So the argument essentially is that you have 3 operators which you put on spheres, and in doing so you are breaking the SOD symmetry. I mean, sphere of course is SOD plus 1 symmetric. You put 2 operators, you are breaking the SOD plus 1 symmetry to SOD symmetry, and you put the 3rd operator and you break it further down to SOD minus 1. And now that configuration respects SOD minus 1, so it better be a singlet under that. So in particular, there could be multiple singlets, that come out of the tensor product of R1, R2, R3, multiple SOD minus 1 single S. And that is a different, so that is a different index contraction having to do with the same operators. And one wants to get all those numbers out of this OPE prescription, because all those numbers are part of the conventional conformal data.
Maybe I missed HOD minus 1 was because you could orient 3 operators in a line.
Yeah. I just said the same thing, but on a sphere. Okay. So the way to deal with these index structures, the best way is to just introduce polarization vectors. So let's say these are indices mu1 to mu(n). So I just make manifest the spin structure. I mean the spin indices here, and nu1 to nu(m) and rho1 to rho j, let's say. And then to each operator, I multiply, let's say, z mu1, z mu2, mu(n). So essentially I define, and O of zx is equal to z mu1, z mu2, and z mu3, and O mu. And I do the same for all operators. And then once I write this 3-point function as a function of z and x, that will capture all of its index structures. Of course, this needs to respect the symmetries of the problem. So z's have to be contracted in a particular way, and so on. And
Some particular dimension here?
no, I don't think, no.
Why? These are not the most gentle operators.
With the spin, with the symmetric traceless guys. Yeah. So for now I'm just restricting myself to symmetric traceless multiplets.
In 3 dimensions, this would be the most gentle.
Yeah. And now let's say you are interested in this 3-point function, and that you can obtain by a 6-point function of phi, because in the OP of 2 phi there exists a symmetric traceless representation. Yeah, I should say that. In the OP of scalars, there can only exist symmetric traceless representation, because if you take 1, 1, and for this tensor product to contain a singlet, this needs to be symmetric traceless of SOD, of SOD. Okay. So this is let's say M. So starting from a 6-point function of phi, I will take this OP limit to recover the 3-point function of O, and I will also get these polarization vectors, because if you look at the OP of phi's,
just to understand that statement, you put all the indices in the special line direction to get your thing. If it happens to be symmetric traceless, you put all the indices just in the
yeah,
special line.
that's right, that's right.
And it has to be symmetric, because otherwise you get
Right. Yeah.
And traceless is just negative.
That's good. Yeah.
And it has to be this kind of vector kind of representation, because you've got just got a vector direction.
Right. Good. You mean as opposed to a spinner? Okay.
In 4 dimensions as opposed to some.
Yeah. Form. Yeah. Yeah. Right. Yeah, that's the part of being symmetric. Okay. So if you do look at this OPE, then you get, let's say, something like that, x mu1, x mu2, x okay. So in particular, the difference between these two vectors serves as a polarization vector for this all. And because we started with the 6-point function, the final thing will be a function of the three vectors, the three coordinates, and the polarization vector will come out of the other three coordinates. Yeah. Sorry to spend so much time on this, if you think it's so basic. Okay.
And sorry, were you going to argue that every 3-point structure that could appear in the product of three of these operators will appear?
Yeah.
That's obvious.
Yeah, that I think it should be. Okay, good. So I hope this establishes that this set of conformal data and the conventional set are equivalent to each other. So you might as well work with.
Now if you fuse two of these symmetric traceless, then in that step you will get
not in sufficiently high D. Because you would still have this constraint, right? You have symmetric traceless, and something which should be. It won't be true for a generic representation, I think.
I just wanted a reassurance that if you do this sufficiently many times.
Yes, that is true. You produce and produce, yeah. Not the next step, but yeah. Exactly, yeah. So that's part of it. That if you are in sufficiently high D where there are complicated representations of rotation group that could arise, you could get to them by considering a sufficiently high endpoint function and taking consecutive OPs. In the first stage, you will end up producing the symmetric traceless representation, which is, if you wish, the tableau of this type. And perhaps, I don't know, you will get another row in the next step. This one has to figure out, but certainly you would extend the set of operators that you could get. And if you keep doing so, you will be able to produce any Young tableau that you want. And that's why thinking about endpoint functions for all endpoint functions is the same as thinking about just the infinite set of 3-point functions, 2-point functions.
So now you never get the spinner type, right?
Yeah, that is true. That is true. I think I want to restrict myself to non-spin. I mean, theories without spin. Unless the generator, I take it to be spinner, but then there are other issues. Okay, fine. So now that these sets are equivalent, what are the consistency conditions? On endpoint functions. So if you are interested in a particular 3-point function as I described, you can get it starting from an endpoint function and taking a sequential OPE. But that you could also do starting from an n+1 point function, n+2 point function. All these things should give you the same 3-point functions. So in particular, this would be guaranteed if you are able to produce lower point functions from higher point functions. So the consistency condition that we propose is that the set of n-point functions is consistent under factorization. So if you could get a smaller point function from n-point function, then this should be part of this set. You should not get something different which is not what you started off with.
A smaller point function of the same.
Of the same scalars, yes. Okay, and what are the possible ways you could imagine such a thing happening? Well, if you have phi of x1, phi of x2, and phi of xn, then you could imagine separating n into n1, a group of n1 coordinates and n2 coordinates. So you have separated coordinates here and here, and then take them to be very far. And in this limit, as r goes to infinity, you should get the correlation function of n1 phi's and n2 phi's. This is also known as cluster decomposition. So this is something that should be respected by this set, that they factorize as you take. If you start with, let's say, what I just said. And then there is another way.
This seems to be significantly more complicated than bootstrap, right? Because, I mean,
Not for
there are so many conditions to
yeah,
verify.
right, but not for the claim that I want to make. In this language, it will become kind of obvious, the claim of things forming vector space. But you are right. I mean, apart from that claim, what would this language be good for? It's a good question, and I would still think that thinking about it would be of some merit. I don't have any specific things to say about it. I mean, this is roughly speaking the way Nima likes to think about amplitudes, where you think about some geometric object in space, this what's it called? Amplitude hedron, yeah, exactly. And then these lower point functions being, some limits of. So there is a huge object, and then as you go to its boundaries, that's the degeneration limit. So here also you can think of this endpoint function as some sort of a huge object parameterized by the cross ratios associated to endpoints, which you can count. And then as you go to degeneration limits, you're going to a boundary of it, and that boundary itself is some sort of a amplitude or some sort of a polyhedron, and then you again go to the boundary of it, and so on. So my hope is that this becomes some sort of a geometric problem. I don't have much to say, much more to say.
In Nima's amplitude and dot at least applied anything for you actually? Yeah, the scattering amplitudes are for all the participating scatters.
Yeah. So
Here you're choosing out just one.
yeah, so it's simpler in some sense even, right? Okay. So apart from cluster decomposition, there is yet another thing you can imagine, which would give yet another factorization channel that you could imagine, which would give you a lower point function, namely the factorization channel in which. So here you could say, if you think of this as an OPE of this set of operators, you are picking out the identity channel. But you could also conceive of a channel in which there is no identity, but rather phi itself. So in that case, in that OPE limit, you will get from n particles or n point correlation function, you will get n1 plus 1 and n2 plus 1. So let me be more precise. If you have, let's say, phi of x1, like so, and then in the limit of this same parameterization, where you take n1 here and n2 here and take the distance to be very large, but not go off all the way to infinity, but rather look at the term which is 1 over r to the 2 delta. So if you wish, that's like there is a blob here, there is a blob here, and then there is a phi itself which is connecting the two, and clearly it should behave as if it's a 2-point function of phi connecting this region and this region, which is distance r, so it should go as 1 over r to the 2 delta, and what it multiplies is the endpoint function here, rather n+1 point function where the other coordinate lives in this set. It could be any of the coordinates of this set, because if you, instead of this point, if you were to choose this point, the difference between them is further ordering 1 over r. So you could just take this to be, let's say, y1. Let me just use y and x times x1 and then y's. And if you do the dimension count, yeah, I think that this is it. Okay, so if you want to reproduce an n1+1 point function, what you want to do is you want to parameterize the coordinates like so with a distance r, and look at 1 over r to the delta term, and that would give you a product of n1 point function, n1+1 point function, n2+1 point function. Okay. Now let me try to get to the punchline in this language. The claim that I want to make, a precise statement of the claim, is that a CFT with a space of theories, space of CFTs with abelian symmetry is a vector space.
So you can bring phi to the lattice operator in the
I will do so now.
But for this
So
claim-
far not.
But for this claim that I think n point function and 1 over r to the 2 delta term in this particular only give me as a
Yeah.
phi term.
You don't need it to be lattice.
But then all the operators which have low dimension, then this phi will also contribute.
Will contribute, but not to this term.
Or to this.
There will be a delta 1, delta 2, and so on. But the prescription is just to pick the particular singularity. Okay. So CFT with abelian symmetry is a vector space. So I have a theory with a Zn or U1 symmetry in mind. And correspondingly, so here I should have mentioned when I say that my alternate conformal data is the set of n-point functions of phi. If there is a global symmetry and phi is neutral, then you will not be able to produce all the operators of the theory through the OP, because it's neutral. Neutral OP will just produce neutral stuff. So you are completely forgetting the knowledge of the charge sector. So when you do have global symmetry, the phi that you want to use should belong to the representation which is the generator of the representation ring. So when you multiply these representations, you should get all representations. The phi should be of that type. But I just want to focus on abelian symmetries. So when you have Zn or U1 symmetry, the phi should be a charge 1 object. So when you take products, you should get charge 1, charge 2, and so on up to charge 0 again, or if it's U1, all charges. Another slight modification that I will do is that instead of considering n-point functions of phi, I will consider correlation functions of phi and phi bar. A bunch of phi's and bunch of phi bars. Phi bar is an operator with charge -1 and same dimension as phi. Now in any theory with Zn symmetry, it's easy to show that such an operator has to exist. That's as follows with the same dimension. If you take Zn symmetry and you take n-point function of phi, this is non-vanishing. If you take any other point function of phi, which is not a multiple of n, this will be 0 because of Zn symmetry. If you take n-point function, then this will not be 0. And now you can take n-1 point function, n-1 phi's on the other side and do the OP. And this OP has to have some operator, which I call phi bar, which has a non-vanishing 2-point function with phi. And that's the phi bar with the same dimension as phi. Okay. in the U1 case also, in the U1 case,
I mean, normal situation, you just say complex function.
yeah.
If you don't want, you allow yourself to.
Yeah, I did.
Okay.
Mm. Yeah. Yeah, I think perhaps you could still say that it's not related to unitarity.
Yeah.
Yeah. Okay. Fine. Now, okay, and moreover, I picked phi to be the lightest operator, and I also want this to be a scalar of charge 1. And then I define Fn to be the endpoint function of this type. And as I argued earlier, this would form the complete set of data. And now I define a Gn, which is equal to Fn to the power alpha, where alpha belongs to C. Now, one can show that Gn also is consistent under factorization. So what I've done here is that starting from one CFT, Fn, I've produced another CFT, which you can think of as, starting from one vector, I have produced alpha times a vector. So I've told you how to multiply. What is a complex multiplication in this vector space? It's just the complex power of the correlation function. And it's the way to think about it is this, because of what I will say next, which is addition. So if you have F1 n and F2n, then I will define a Gn which is equal to F1n times F2n. And this would be V equals V1 plus V2. And as you can see, that this distributes over this product just the way addition multiplication distributes over additions.
It's like log of Gn.
Log of Gn is a vector space. Yeah, actual variable, vector-like variable. Exactly. Okay, so perhaps this is somewhat obvious that this would have to work, because you have a CFT1, you have a CFT2, and when you take products of endpoint functions, essentially you are exploring a sector of the direct product conform field theory. So Gn would have to satisfy the axioms of conformal field theory. But what is non-trivial is that such a Gn also does satisfy the factorization. And the way to see that is the following. Now, I talked about two ways one can produce lower point functions starting from higher point functions. One where there is an identity. So
By this logic, Fn for 0, all Gn equal to 1 would play the role of the
identity, zero vector. Yeah. Right. Right. 0 times V is 0 vector. That type of okay, and okay, so why is it that this Gn satisfies factorization? So you could think, if this alpha were integer n, then again what you are doing essentially, you're taking m copies of this CFT and just taking the direct product and looking at a particular sector of this direct product. In that case, you do expect that this Gn would be a correlation function in a conformal field theory. But the non-trivial part is that even when that power is fractional or even complex, this set of correlation functions satisfy the factorization.
No, so a tensor product, right? So there, fn square, or even the downstairs here, fn of 1 would have been a function of x1, x2 up to xn,
Yeah.
and fn of 2 would be a function of y1, y2.
No, the same points, same points.
That's right. But with the same point, I don't understand the direct product thing. I mean,
Well, that's how the direct product works, right? So let's say fn is a correlation function of some phi 1, right, at x1 and so on. And then this guy is a function of phi 2, and then this would be the correlation function of the composite operator phi 1, phi 2. And because they don't interact with each other, when I compute the correlation function of these guys, I just compute them separately. And that makes them at same point.
Doesn't this operator have charge 2 under the U1?
No, I define this to be a charge 1 under the mu 1.
Then what about the operator phi 1 times Zn?
Yeah, so those operators are not present in this. This operator, this is not a direct product operation. This is the sector of a direct product theory. So yeah, the sum sum of vectors is not the direct product. It just picks out a sector of the direct product theory.
this product should have been a two-part theory. Maybe where the
No, well, I just mean you have a CFT1 and a CFT2. And operators coming from CFT1, let's say, is phi 1, and the operator from CFT2 is phi 2.
And you would call that, I mean, I would have called this thing as O of x1 and x2 equal to phi 1 x1 and phi 2 x2.
He chooses to put them together.
You choose that.
He wants local.
I want a local operator.
And in terms of the vector space, you're saying that this operation is like a tensor product. This is what I'm not understanding.
No, at the level of the vector space, this is direct product, direct sum. This is just sum of vectors.
This is direct sum.
It's sum of vectors. I should say just the sum of
Yeah,
vectors.
because it's all
It's happening in the log, let's say.
So now, in the case that it was Zn,
Yeah.
then this is charge 2 under Zn.
No, this would again, so okay, I should mention that you could do this operation here of adding the two vectors associated to even different symmetry. But if you put them to be Z, if you take both these theories to have a Zn symmetry, then I call this guy to be the generator of the new Zn.
Suppose n was is n prime.
Could be or not necessarily.
Suppose n was 9.
Yeah,
Suppose n was 4.
yeah.
Then what under the original Zn this is Z2. So you would never then generate
No. No. So this one was charge 1 under Z4.
Yes.
This is also charge 1 under Z4.
So now total.
So if you take this to 4th power, this would appear 4 times, and that would have an identity, and phi 2 4 times, that would also have an identity.
Right, but if you put the second power.
Yeah, that would not have identity. So exactly, if you look at the orbit, it's 4-fold. And if the symmetry were Z2 and Z3, this would be a Z6 symmetric theory, because the 6 products of these things would have an identity in it. So some sort of an LCM of n's would be involved. Okay. So let me show that this is the case. The argument is quite simple. The argument has to do with the homogeneity of these factorizations, and the fact that this is the lightest one. So let's first look at the factorization in which there is an identity, so the cluster decomposition. So you have a set of operators and in the channel when there is an identity goes as set of n1 point function and 2 point functions plus 1 over r to delta some other 2 point functions and so on. Is this clear or am I being too schematic?
Yes.
Okay. So this is just the OPE of N1 and N2 decomposition, and in this case I have an identity operator. In this case I have an operator of dimension delta and so on and so forth. Okay, and that is my Fn. And now what is Gn? Gn is this to the power alpha, wherein I take this sum to the power alpha, and because the identity is the lightest operator in this channel, the way this behaves at long r is that you can pull out this to power alpha, and then you have 1 plus dot 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 to the power alpha, and this would just expand in a binomial fashion, while the identity term will simply go as a product to the power alpha, or this to the alpha and this to the alpha. So what I've shown here is that starting from an n point function to the power alpha, you get an n1 point function to the alpha and n2 point function to the alpha, the way the requirement that was supposed to be satisfied by Gn. So this happened in the identity channel, and in the another channel where there exists a phi, I have ensured that the phi is the lightest operator, and that's why the leading term is the one in which there is phi mediated. That's where phi being lightest is important. So in that case, you will exactly see the same thing, except that, so let me just modify this, except that the first term will not be identity simply. Yes? Someone tried to speak. Okay. Except that instead of the identity, this is a term which is mediated by phi. So he says dimension r to the delta phi here. And in the rest, there would be higher terms having to do with higher operators. But the point is that this is a charged sector. So the operators that are flowing in, I have charge 1. In particular, there is no identity operator. That's why this does not start with even a more dominant term, which is identity. That is absent because we are looking at the charge sector. The crucial thing is that this expansion starts with the charge sector. And now when I take the power alpha, the same thing goes. The leading order term just comes out and becomes 1 over r to the delta phi times alpha plus 1 plus dot 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 to the power alpha. Sorry, this was this. So clearly, so this will expand binomially. So you have 1 plus dot 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 stuff with some alpha dependent coefficients and so on. But the leading term is this, which is the term coming from the mediation of the leading operator. So again, we have shown that starting from g to the alpha, in the limit where there is phi, you also get alpha powers of the correlation functions. Here.
And why is alpha delta phi
The correct thing, yes, because as soon as you take n point functions and take its power, the homogeneity changed. The 2 point function, yeah, the scaling dimension is multiplied by alpha, and you expect exactly the same weight here. Okay. So these two observations tell you that this is a vector space.
And you showed the leading terms was outside.
Yeah.
And what about the sub-leading terms?
So subleading terms will define the new, the new OP coefficients and so on. So let me give you an example. So, let's start with the free theory, or even the generalized free field theory that I talked about, where you have phi of dimension delta, and then all endpoint functions are obtained by Wick contraction. So this is, you know, so let's see here in points.
You say you know nothing about the subleading terms because you only knew what happened when they were all.
Yeah, yeah, exactly. So they are
So
free to
there's no
do
check on that.
free to do whatever they want. The check was in the consistency condition that should produce the same endpoint function. Fine. All these things give you 1 over x to the delta type of 2 delta.
And in a sector where identity is produced, the phi cannot also.
Yeah, because it's charged. Exactly. So one could have naively thought that you know, taking this alpha is simply an analytic continuation of the multiplicity. But if this this is indeed true, but that cannot be applied to theories, let's say, without any global symmetry. It doesn't even make sense. If it does not have global symmetry, so the OP is not constrained by anything. In the channel of phi, identity can also appear. And then this will not be a consistent construction. So you cannot simply say that this is just analytic continue. You take the theory and analytically continue in N, which is the multiplicity. Okay, fine.
Something in this intermediate operator has charged.
Not in the same channel. You know, the charge of the operator is always determined by what I put here and what I put here, right? By conservation. This better be charge -1 for this to be 1. And if this is so, then the charge 2 can also not be produced. Also charge 2 cannot be produced. Charge 0 cannot be produced. Only a fixed charge guy will be produced. These are essentially some of the problems that you would face if you were to try to generalize this for non-abelian symmetries. Because you know, in the direct product of a bunch of non-abelian representations, multiple representations can appear.
So what about a phi and a phi bar?
Phi bar? That would be neutral, right? So that's the identity channel.
Right. But is your set of correlation functions all correlators with phi and phi bar?
Yeah, but phi bar is a different operator, right?
Ah.
This was just phi and phi bar.
Yeah.
Okay, so let me just mention some of the observations that.
For the subleading terms,
Yeah.
so you would say that you can always invent your CIJKs such that subleading terms work. Is that
Yeah, subleading terms will give you new CIJKs. You can just read them off.
you can say them off, and whatever your initial choice of number of insertions where the same CIJK will always get from whatever you use.
Yeah, so the consistency condition was, this came about by requiring that you got the same CIJKs coming from any endpoint function. So in particular, if you want a CIJK having to do with phi going to some O, that you can get by starting from 4-point function and decomposing it in this channel, let's say. And that 4-point function is the original 4-point function to power alpha. And now you can just expand it and read off the new CIJKs. So that would essentially be the old CIJK times some sort of an alpha times alpha -1 divided by 2, roughly. This type of, you know, things will be multiplied by binomial
But in this
binomial
one,
terms.
in this one in which an O appears in the beginning,
Yeah.
why is that dominant?
It's not dominant.
So it would be, it could have some lower, so I mean, here also you're going to do a binomial, no, sorry.
No, here also, yeah, you would have to, so because, you know, this inside the bracket goes as a sum of, let's say, sum over O, C phi O squared FO, right? That's the standard form of this thing. The question is, what is the leading order guy? Now, if this, so for that you need to be careful and say exactly what we mean by this. So these are charged objects, so we could either do phi bar like so. In that case, the leading order guy is identity. So
Phi and phi bar.
yeah, but Yeah, but first let's do this,
Okay.
and then you have this to power alpha, and that would give you 2-point function phi bar to power alpha having to do with identity plus 1 plus you know C phi let's say O, the next guy. Well, there will be like alpha here having coming from here, and FO, right?
Yeah. 355. Okay.
Yeah.
Yeah.
So essentially,
Some additional
yeah,
power of
alpha minus 1 by 2, and then so on, right? C phi. Yeah, there will be a bunch of terms coming from this.
Well, whether at this level you have the next order in the binomial for O, or whether some O prime, so at the subleading order it's not clear whether the next important term is the one that you wrote. But
No, that is true. What you're saying is true. That the leading order, I mean, the after one the subleading order term will be of this type, but after that there will be some mixing.
yeah, mixing, yeah.
Right, O square will mix with O2 and so on, right? That's kind of, so indeed the spectrum of theory is not going to be the same as this. So whatever sum you get is not going to be the sum over these original O's. There will be lots of new operators that would come having to do with O squared and so on, which would all disappear in the limit alpha goes to an integer. So such operators are usually called these evanescent operators. So when alpha goes to an integer, you expect sorry, I should backtrack a bit. If you start with an unitary theory and do this construction, because of these binomial coefficients which are of this weird type, clearly that does not respect the reality of squared, positivity of the squared, C squared, right? But if alpha were to be an integer, you know that this is just a tensor product and the theory better be unitary. The resulting theory better be unitary. So what happens is that you have a bunch of operators with a bunch of OP coefficients, and in the limit alpha going to an integer, some of those coefficients cancel, become 0. So the non-unitary operators that were introduced, they just become null in some sense, or their OP coefficient goes to 0, and you recover unitary theory. Sorry, maybe I ended up saying something that you had not asked about.
Yeah, you're saying there could be some negative, at the next order there could be some negative guys.
Yeah, even if you start with a positive alpha, then binomial coefficient, because it doesn't terminate, will produce negative. And then in order to read off the spectrum, you really have to rediagonalize in terms of conformal Casimir, and get to a new basis of conformal blocks.
And all this stuff can always be done. I mean,
Yeah.
Suppose you get a C phi O from one correlator, and the same C phi O from another correlator. Will you say they will be the same?
yeah, that's.
It's not clear it's the same O because all we know is dimension. But so maybe I should ask that. At any given dimension, is the operator unique? If you were to unravel the operator spectrum of your theory, would you get high degeneracies in order to make this work?
Yeah, the statement about degeneracies is true. You will get degeneracies, but I don't know how the degeneracy will increase with delta.
With sufficient degeneracies, you can always get this. Because the one operator we can change here, the only the operator. Okay,
Maybe I'm not.
So maybe the more general question is that you're postulating some new 3-point function, and then it has to work for all correlations. And is it clear that
So in the new theory, right? No, I think, yeah, I think so. Yeah. Yeah, I think that, I think there should be a simple argument which suggests that that's, don't have it with me now.
I think for the leading term,
Mm.
it's sort of clear.
Mm.
Because it's always the thing that was the same raised to the power. So the binomial thing will always be back.
Mm.
Right? That seems reasonable. It's less clear to me somehow for the next term. But
Mm. Well, so the way I motivated this construction was by introducing a set of consistency conditions on the endpoint functions of phi, right? I said that if the lower point functions are consistently produced from higher point functions, then any way of getting a particular 3-point function should be the same.
okay, so
And
that
here-
condition is clearly okay.
Yeah.
But is that condition sufficient? Because as you explained to us, that basically in this case has been the union.
No. So now you think, now you apply the same statement for the for this new theory, and now here also I have given you an set of n-point functions, and if they do work out, then the rest must.
I suppose then maybe what I didn't understand is why your postulated condition. Your condition was just that when you produce 5 correlations,
Yeah.
then they're all good.
Yeah.
Perhaps my question is it clear that that is sufficient?
Yeah. No, that's a good question. I don't have a rigorous way of showing that this is a sufficient condition. Because what is clear is that if let's say if you start with a particular OP channel, and you are interested in this 3-point function, let's say, of some O starting from 5, 5, 5. Okay. Now in this OP channel, if there were to exist a phi, then you could simply cut here, and then realize that this OP coefficient will be the same if you were to consider the lower point function as well, and then the check of the previous statement of getting this correlation, this OP coefficient from the bigger one, just ends up being getting the right lower point function from the higher one. But you could imagine what happens if there is something else here, phi prime. Now it's not immediately obvious that you will get the same. In fact, the question itself is not very well defined, because you can evaluate this OP channel, but you don't know what these OP coefficients are. So according to this, they will just adjust themselves. The question is whether this adjustment is consistent with.
But perhaps the question is, will you in this process end up postulating an infinite degeneracy per dimension?
No.
At least for
No.
this theory, you can say this is
No.
not the case. It's always random.
Not per dimension. Maybe you want to say as you grow in delta, the degeneracy grows somehow, in some way. That could perhaps be true, but certainly not for any dimension. Not for finite dimensions. You don't have infinite degeneracy.
You can actually evaluate
Yeah.
the whole spectrum, and that is always finite. It will go higher, but it is finite. For this example.
So already that tells me that my main one is somehow I can't even see.
But it does grow.
It grows, but I was even worried about like some
No.
finite dimension.
No. Okay. Fine. So now let me just say that you could do this construction of a generalized free field. So in particular, the familiar expression u to the del 1 plus u to the delta plus u over v to the delta is the 4-point function for phi of delta. For delta equals 1, the theory has stress tensor. And this is just the free theory. These terms are nothing fancy, but they just include Wick contractions of 4 points, which are, one is like the identity channel, which is this Wick contraction. The next is U, which is this, and then the other one is this guy, which is this. Okay, you can just see written in terms of cross ratios. There is a prefactor here to take care of, but written in terms of cross ratios, it's just this. And that so clearly this is like a free theory, but now you take this 4-point function and enumerate the spectrum of operators, and you see that at spin 2 you don't have a conserved current. So that means the theory is not local. And as you said, delta equals 1, the current comes down and becomes the stress tensor. Okay, and that is familiar, because this then just becomes the free theory, because phi contract like a dimension 1 object. Sorry, I should say I'm in dimension 4 now. More generally, this should be whatever, d minus 2 by 2. When phi hits unitarity bound, it's a free object, and then it better have free correlation functions. Now, what our construction proposes in this case is to take this whole thing to power alpha, and also realize that this is also a non-unitary theory, a CFT. So in particular, you could do this in any dimension, and this way get somewhat non-trivial CFT in any dimension, a non-unitary. But now there is a puzzle here, the following. So if you set with this alpha present, if you were to set delta equals 1 and enumerate the spectrum, you do find stress tensor.
That's in the phi bar.
Hmm?
Phi bar, so this is the stress tensor, and then when you take some correlation,
Yeah, it doesn't change.
Alpha.
Yeah, exactly. So you do have stress tensor. In fact, just like the free field theory, you do have higher spin currents, precisely because of the reason that Chirag mentioned. Because you have a 4-point function which you want to expand. The leading term, which is just the identity, gives you just a 2-point function, appropriate dimension of phi's, and then the rest does not alter any conformal dimension, but just gets a factor in the front. So that preserves the existence of stress tensor and higher spin symmetries. So what is the conclusion? The conclusion is that the theory with this 4-point function, where delta is set to 1 with power alpha, also has higher spin symmetry. Now, Mallasena and Chibodo point out to us that unitary theories with higher spin symmetries are free theories, and this clearly gets by because it's not unitary. But it's instructive to see what exactly happens. So in their paper, they have an argument where they take the Q4, the spin 4 current, and act on phi to see what happens. And in this case, unitarity says that nothing else can happen, but you have to get a descendant of phi, like so. There is no other right operator, the right quantum numbers that lives here. And because this is the case, then this implies that the 4-point function of phi, when you can just starting from this as a symmetry, using the word identity for this Q4, you show that the 4-point function of phi has to be a Wick contraction. Now clearly, our 4-point function is not a Wick contraction. It has a Wick contraction to power alpha. So how do we get get around this argument?
This argument was made in the case where alpha had phi had dimension
1. Yeah, right. In 3D, yeah. That's right.
How will this imply a contraction?
Because you write it in momentum space, phi p1, phi p2.
Yeah, Coleman might do that.
Yeah. but to see more directly, this is simply a p cube, p1 cube plus p2 cube plus p3 cube plus p4 cube equals 0, along with sum over p's equals 0, and that gives you pairwise, yeah.
The same thing Coleman will have that with calculation. But not linear.
Okay. Right. So the way this works out in, I mean, the existence of fourth spin 4 charges as consistent is essentially by having another operator here, a different operator that could appear on the right hand side. In Maldacen and Gibaudo's case, the unitarity essentially restricted the form of the operator to be this, and that's why all these arguments could go through. But in our case, if this were true, then a new type of operator has to appear here. And this operator has to have, let's say, spin 3 and twist 0. That's what this operator was. The charge has twist 0 and phi also has twist 0. Sorry, wait, what? Twist. What do we want here? Can you remember? Right, but this here has twist 1, right? This is twist 1. Sorry, this has twist.
I has a given twist and Q has 0 twist. So the whole operator on the left hand side has the twist same as phi.
Twist same as phi, right?
So right hand side you want an operator that doesn't have twist.
And then minus has to the equal charge.
And moreover, this operator is odd under Z2. So we should be able to see this operator in the operator spectrum. So if you take the 4-point function of phi, which is the contracted 4-point function to the alpha, and then enumerate the operators, all the operators that would appear here are even. In order to get an odd operator, what you would have to do is you have to start with something which is an odd, even, odd, even. Now, in order to get this even, you have to start from something that is odd, odd. Well, that is you have to start from something that is phi o. Like so. So you could start essentially from the 4-point function, 6-point function of phi, and do the OP to produce a 4-point function of this type, phi e, phi o. This is a Z2 theory. So, yeah, mean field theory is always Z2 symmetric, right? So you take this 4-point function and now you write it as sum over states, and the states that would appear here are odd under Z2 because this is odd times E1. And now in this channel, you realize the first operator, of course, is phi because that's the lightest odd operator, and then there are other operators. And if you look at the operator of spin 3 that you want here, you see that it has exactly the same twist as phi. So that's a candidate operator that could appear on the right hand side of Q4, making the higher spin structure also consistent. So this was just an example where you can do explicit computations and get higher correlation functions, all the OP coefficients.
And you can distinguish that operator from del minus E phi because it's not a descendant.
It's not descendant, it's primary.
Yeah.
It's primary. So yeah, okay, let me stop here. Thank you.
HRI questions?
so far I did not talk about. So far I did not have any large n type of counting. This was for general conform field theories. So perhaps you could clarify the question.
Like what I meant was, suppose you have matrix operators.
Yeah.
You don't have to get large n. You have to have multiples, right?
Uh,
If you have pure one, of course you have single operator. But if you have a matrix operator,
okay.
a matrix field, then phi square square versus phi to the 4 would belong to the same summation set for as far as given charges are concerned.
Yeah.
Right? But you may have articulated, you may have linear.
Oh, you are saying. I see. You are saying maybe that the generator that I took phi could end up being degenerate.
Yes. So you may have operator mixing also at quantum level.
No, yeah, I am, I guess, assuming that there is a unique lightest charged operator.
I see. The other question was about this not having stress tensor. Couple of things. First is that how do you couple a theory like that with to gravity, for example?
No, you cannot. I don't think you can. That's what leads to the nomenclature that such theories are non-local.
Okay.
You can't put them on arbitrary background.
You cannot, yeah.
You can't put them on arbitrary background, right? Okay. And also, what is the notion of secondary? Typically, at least in the 2D CFT, secondaries are defined as OPs of stress tensor with primaries.
Secondaries, descendants. Descendants, I just think of as as something that you get by acting on primaries by derivatives.
Well, that is only one class of descendants. Right? I mean, if you have conformal symmetry, you have a much larger set of descendants which are beyond derivatives.
Sorry, in 2D, right?
Yes.
By acting with L minus N. Hierarchy, yeah, but in non 2D you don't expect, you expect all the descendants to come from derivative action.
Yeah, true. Okay.
There's no one that actually gets it. Okay. TIFR question. One question that I asked you guys before, which I mean, some months ago, is suppose you take this theory to the power alpha, or the alpha times the vector. Can you say anything about the partition function of the theory in terms of theory to the power? Partition function, let's say, on T4 times S3 times
Yeah. No, I think it would be quite difficult to say. I mean, what it would involve is essentially enumerating the 4-point function and then just summing over all the states.
You might naively have hoped that your prescription, which said any number of insertions of phi that goes to the alpha, would map over to zero insertions of phi. Now I know that's an issue of normalization.
But that's on R4, right? Yeah, it's thermal. Maybe one wants to say something about thermal correlators and then take 0-point limit and so on.
Right. Okay. So maybe that's another question. So this prescription would not work on S3 times S1. So suppose I try to compute the correlation functions of the same theory on S3 times S1. In the case where there's a stress tensor, that makes sense. Would the same prescription on S3 times S1 work? Or
the same prescription need not work, right? As long as you can make sense of the theory, as long as you have some prescription which is in some sense consistent. So now it becomes a question of how do you relate the two, and what what do you expect? I guess you expect that in the zero temperature limit you get back.
But it will not be just taking the correlation functions of the original theory and taking that to the power.
Probably not. Yeah, but it's a good question to even ask whether it's consistent. Whether there is a way of defining it, and how to make, how is it that they're consistent with flat space correlates.
Yeah. It should also be consistent with the S1 string integrity.
Mm.
There you have another string which will be the same description for that.
Yeah, I don't know whether it would be the same prescription.
But it will be some.
It would be some theory whose correlations, yeah. I mean, there the way of doing these vector manipulations would be different. Probably. I don't immediately see that it would be the same construction.
For alpha of what?
Yeah.
Specifically, according to.
Yeah. Not free field. This was just an example. The construction was general for general theories.
In the case that you had alpha equals an integer, so that everything is maximally good. Here what you're doing is taking the product and then taking some orthopoid of that.
Even alpha equals integer is like that.
Yeah.
Yeah.
So if I understand right, let's say we had a U1 charge in both. Then the product theory would have a some U1 charge and a difference U1 charge.
Yeah.
And you're restricting to the charge 0 under the difference.
Yeah. Yeah.
So it would be like taking that product theory and orthopoid.
Yeah.
Now, even this it's not totally clear that would give you a well-defined conformal field theory overall.
Yeah. Yeah.
It's like restricting to some singlet set, which you said right at the beginning of your talk was not clear. It gives you something like that. Right? I mean, of course, it gives you a good solution to bootstrap.
Yeah. Yeah, that is true.
So even in the case that the integer, something may go wrong somewhere. It would be nice to identify whether or what. And in this case, in the case that it's integer, then this question about the partition function should be used up. Right? Because if we take the partition function with the chemical potential for the first
both
U1,
U1s and then
the chemical potential for the second one.
just take the singlet.
Exactly, and then just take the same.
Yeah.
I wonder whether something like that, whether that would give you a clue to what might be the generalization generalized.
I think though it's slightly if you just think in terms of this yeah, okay. Sorry.
Yeah, I mean this would be the statement that, so suppose we break the first partition function with z to the power q1, z1 to the power q1 and z2 to the power q2, and then you want to pick out all things that have homogeneity 0 in z1 and z2. Right, something like that. Which you could get by some contour integral.
Yeah.
Now, could it be that same contour integral gives you the right partition function for Z1? Or something like that?
Yeah. Yeah, that's a good question.
Okay, more questions?
F1 to the power alpha 1 times F2 to the power alpha 2. That of course is the vector space of
Yeah. Right, because how to take product with alpha and how to add these are the two basic operations. And that's the most general operation. Yeah.
The delta phi will become delta phi times alpha 1 plus alpha.
Hmm.
You think of it as two-step process.
Hmm.
First you produce the to the power alpha 1, then you produce the to the alpha 1, then you.
Hmm.
Except that it is some strange log stuff. I mean, yeah.
But if you buy the argument that you can take to the power alpha and you can multiply, then you have to do it.
Yeah. To the power alpha is any theory.
Yeah.
And then in that theory, I'm just.
Exactly.
Yeah, exactly.
And about the literacy thing, so I take a phi in one block and phi bar in the other block. So what comes in the middle is some spin through guy.
Yes.
Right?
So
Now,
for that, I'm not saying anything.
yeah, I'm not saying anything,
Yeah.
but I'm saying that, for example, if you look at the subleading term,
Hmm.
then it will suggest some dimension of that spin through charge through form. I mean charge. So it will give you some dimension of the charge field, right?
Hmm.
If you can just read off the power
Yeah.
1 over r to the power whatever that thing is, and then you can get charge to in other ways, 3 phis and 1 phi bar in one block,
Yeah.
and so on,
Yeah.
and that will presumably give you some other dimension, 1 over r to some other power. So the charge to operators here would have some other dimension. But presumably you would say that there are so many operators.
No, I think in this case you'll just get the same operator, same
You get the
dimension.
same?
Yeah.
I see. There.
Because in the original theory you got the same.
In the original theory,
Before taking to the power alpha, you got the same.
well, I'm going to strange binomial.
Yeah, so but the dimension will not be, the coefficient.
Yeah.
It's right there. Okay, dimension. Okay, good.
There's a comment that I wanted to forgetting.
Oh, wait. The dimension is not going to change, but it's the interpretation of this dimension is different now, because earlier it was twice delta phi, so 1 over r to the power twice delta phi minus delta O. That's what would have appeared earlier,
Mm-hmm.
right? And whatever power of 1 over r that is, you would identify that power to be twice delta phi minus delta O. Correct? Now it's some twice delta phi prime. It's a new delta phi now. Okay. So now your delta O would be something different. You can still, of course, invent it.
I can, because it's a leading guy, it's bottom.
Yeah, it's leading guy. It's the leading
Not a
guy.
subleading guy.
Yeah.
So it's true that nothing to do.
No, in the leading guy you will get just
No,
the
I was
alpha
thinking of
times.
subleading guy. But the interpretation of the subleading guy is now different, right? I mean, I have phi O, where O is a charge to charge minus 2.
And what was the leading guy in this term? So there was an O and an O prime?
Yeah, you could say that you are looking at a subleading guy.
Yeah. Let's say there's a leading O and then there's a subleading O.
Right. I see. The charge to fellow is the leading fellow.
We could choose to look at leading or subleading. I think the leading guy will just get the dimension which is the old dimension to the power alpha times alpha
And in every correlator.
in every correlator.
Happens.
Yeah.
And the subleading guy will just be
Yeah.
relative to that leading guy, the same.
It's integer separated or something. Yeah, sorry, yeah. So, yeah, it is of course not clear what these statements would be good for. Just a statement about the space of non-unitary solutions to the non-unitary crossing equation, non-unitary solutions to crossing equations. So let me make the following possibly incorrect conjecture. So if you start with unitary theories, there is an operation that will respect unitarity, namely taking integer powers of these correlators and multiplying them. So it's a vector space, let's say, over Z. which would respect unitarity. So in other words, unitary theories would form a lattice, because you can take CFT1 and CFT2 and make sense of m times CFT1 plus mn times CFT2. It's still going to be unitary. So in the space of generically non-unitary theories that I just talked about, unitary theories are some sort of lattice. And then you could ask whether the rank of that lattice is the same as the dimension of the vector space. In other words, whether the lattice spans the whole vector space or not. If it does, then the statement would be, the non-trivial statement would be the following, that all non-unitary theories are linear combinations of unitary theories. And it could be true or false. I don't see a easy way of showing one way or the other.
Wait, but now, when you say theory, you're just saying solution to the bootstrap again.
Yeah.
If you want more than that, then even this lattice is suspect.
Well, I mean, the whole bootstrap program is based on that, right? Presumably, once you require unitarity, no additional conditions are required somehow.
Well, you
At
gave
least
a
in
counter
higher,
example at the beginning of your talk.
at least in higher dimensions. I don't know.
Not so clear, right? If you just restrict to singlet sector of some group,
Mm.
and that's essentially what you're doing if you're on the TP-TIFR stuff. I mean, if you really take direct product of the theory,
Mm. If you take Z and normal poles and so
if you take this particular
Yeah.
restriction, it's not totally clear to me.
yeah. Let's just say solutions to the
Bootstrap.
unitary solutions to the bootstrap.
Yeah. But related to that, I was wondering about the following. Let's restrict attention for a moment to theories that have a stress test.
Mm.
Okay? Now, I was wondering whether, okay, it's just a random statement because I don't know how to take it, but let me just say it anyway. You know, there are these unknown other constraints for features.
Mm.
These unknown other constraints may have nothing to do with unitarity. Because like modular invariance is not obviously anything to do with it. Right? Just replacing this factor with that.
Mm. Presumably, Lee Young model is.
Is
Yeah.
modular, exactly.
Mm.
So I was wondering whether imposing these unknown other constraints might give you a significant cover. And the motivation for that is that it's possible that even your integer values fail those unknown other constraints. Now, this might be important because in a condensed matter system, let's say in a lab system, the theory that arises may actually be required to satisfy all these other constraints.
Yeah. Yeah, certainly. Yeah. Yeah.
So could it be that there's a large other set of constraints on this manifold coming from?
No, that is certainly true. I just don't focus on
You
it
don't
because
know.
I don't
Yeah.
I don't know how to
Yeah.
think about these constraints, especially from the point of view of a local operator language.
Right.
That's an interesting question by itself, I think, to figure out these other constraints.
But it's physically very important because this large degeneracy that you're saying seems to spoil universality, at least for non-unitary theories in the most.
Mm.
Because it could flow here or it could flow here. No two experiments will give you the same particular
Mm.
exponents unless there's very particular reason.
Mm.
So the question of restoration of universality
Mm.
may be related to this.
But why doesn't it happen in the case of two dimensions where you have multiple non-unitary theories, even modular invariant, coming from, let's say, the Coulomb gas?
I don't know.
but
But you could ask even with unitary theories. You could ask why let's say Costello equality. Three boson and a circle,
Yeah.
circles of different sides.
Yeah.
And then we know. It's true that in 2 dimensions, XY model is just not a variable. Right? You change the parameters a little bit, it flows to a different.
Mm.
So perhaps that's just the same thing. I mean, maybe 2 dimensions is slightly. Or K3, right? You've got a K3 compactability.
Mm.
Compactability, you change the model. I think that's just true of some systems.
Yeah.
But as you said at the beginning, in higher dimensions,
Yeah, I
But
think,
predicting
yeah.
lack of universality and also very important.
Yeah, for that we should understand what a CFT is.
Yeah, that would be nice to know if there's some experiment to do. I mean, is it true, for instance, that when you go away from universality, unitarity, maybe somebody's already made this statement by doing some language. Maybe you haven't clearly explained. No, I don't know. Like Abhijit thing, it sounds like an interesting and open question about what are the full set of constraints altogether, or what in addition you should check. I suppose some sort of modular.
Yeah, so let's assume modular is management can you like,
What do you mean? Let's what do you mean?
suppose you are expecting that there will be modular in management in defect.
Yeah.
If you assume that, then is there a simple sake of doing that other than explicitly computing the partition function?
Yeah, I suppose what you want to know is how does that check. I mean, the great thing about two dimensions is that the operator spectrum allows you to compute the partition function on a surface. Here, the operator spectrum allows you to compute the partition function on a sphere, and unfortunately, a sphere and circle are not the same. I don't know. I mean, it's a great question.
My suspicion is that it somehow has to do with the spectrum defect operators
Yeah,
in CFTs. Yeah. So if one could lift this vector space structure even to include defects, assuming existing OP defects, whether there is a consistent defect OP. I mean, it could be that the first assumption itself is false and that defects play only a minor role. If they really are.
You want the thing, the operator that will be dual, let's say 3 dimensions. If you find some operator that is dual to states on T2.
Yeah, so that's certainly not defect also, right? There is no state operator correspondence. But you could, I mean, the way I'm thinking about linking topology and defects is the following. So in 2 dimensions, we could either study the partition function of torus, or we could study it on a cut sphere, right? So that's a sphere, and you insert twist operators that produce a cut. And these twist operators exist in the tensor product theory. 2 copies of CFT, let's say, will have a monodromy, which in the permutation space, in the permutation group, and that would give it the 2 sheets that are connecting. And then computing the correlation function of such 4 defects along, because these kind of disorder operators, you are discovering modular invariance. So in higher dimensions, these defects are to be thought of as co-dimension 2 defects. Some lines in 3D, surfaces in 2D, and so on, 4D. So making sure that somehow their correlation functions are consistent should be a way of thinking about, let's say in 3D theories with S2 times.
In higher dimensions, actually high dimensions, if you want to turn an S2 into a 2.
No, so let's see. So if you have 3 dimensions on S3, you put these circles, 2 circles. Now what will you get? So it's essentially, I mean, essentially the following. You have 2 S2s, S3s, and now you cut holes along along these circles. Yeah, along not the circles, the whole sheet. So let's see. Yeah, exactly. So you would get S2 times S1 there, but if you do more, you will get other handles, more handles. So just imagine S2s and then a picture looks very similar to 2 dimensions, but this is what it will give you, I think, if you more and more cuts or more fold cuts. I don't think there are names for these manifestations. codimension d minus 2. No, codimension 2.
Right, two dimension.
Codimension
Right,
2.
Yeah, correct.
And exists in a tensor product theorem.
Yeah, that's d minus 2 then.
Yeah, yeah, right. And having a consistent defect in local operator algebra, hopefully, it would be nice to show at least that having a nice algebra of operators with these defects ends up making the CFT partition function consistent on these surfaces.
That would give real rationale to that.
Yeah.
I think we sure we hope you will not done. In 2 dimensions, is it clear that that's taken? Then the defects are just falling.
Yeah.
You have to say which the defects you want your motivations were defects in all the whole.
Yeah.
So that's what you have in mind here.
Yeah, yeah, yeah.
Okay. Okay, so then.
Yeah, that's some monodromy in the permutation space, permutation group.
Right, because as you say, if you do this thing in 2 dimensions, you get a torus partition function.
Yeah.
The torus partition function is ill-defined.
Yeah. One slight issue that I have is that if you do this construction on the sphere, you get the angle to be 4 pi. So it's some sort of, it doesn't seem to produce a nice flat torus, but torus with some axis angle at 4 points.
In 2 dimensions or high dimensions?
In 2 dimensions also. I mean, if you map this cut sphere onto a torus and look at the orbifold points, there's a 4 pi angle, right? So somewhere on the torus there should be a 4 pi.
But now there's this, topologically it's a torus.
Topological torus, yeah.
So every torus that's topologically a torus is a Y factor times a torus.
Yeah.
And then it's a question of getting